Okay, this second part of 7.2 with graphing absolute value. The first part we just kind of looked at the general form, some of the characteristics of it. So now we're going to put some pieces together. So the first part here says, oh, this should be y is equal to a, whoops, a times absolute value of, oh no, I had that right. Absolute value ax plus b. Okay, so what happens then when you have that absolute value inside, or that a value inside the absolute value? It says, notice the a value is inside the absolute value. If this is the case, the absolute value should be graphed using a different method than what we did in the last section. So example, sketch the graph of y is equal to the absolute value of 3x plus 1. So first what you want to do is we want to sketch the graph of just plain old y is equal to 3x plus 1. So our y-intercept would be at 1. Our slope would be 3 over 1, because we'd be going 3 up and 1 to the right. So we sketched that first. So my y-intercept was at 1, and then I go up 3 over 1. And then I could continue, I could do a couple more just to for you to see where the excuse me, where the points would end up. So up 1, 2, 3 over 1, up 1, 2, 3 over 1. Okay, so we have our graph, so our y-intercept is at 0, 1. I drew that in there, so there would be that line. So I would go like this. Use your ruler so you have nice straight lines. That's what it would look like. So then it says calculate the x-intercept by setting y equal to 0 in the absolute value equation. The x-intercept can also be located graphically from step 1. So what I could do is I could extend my line and go down 1, 2, 3, and then over 1. And you could from there calculate where that would go. I'm just going to erase that part because I don't want to show that quite the way I did there. 1, 2, I'm going to do some different color dotted line. Okay. But to do this by calculation, we put 0 is equal to 3, absolute value of 3x plus 1. So 0 is equal to 3x plus 1. So that would mean that, I'll just finish this here, negative 1 is equal to 3x. So if I divide by 3, negative 1/3 is equal to x. So by looking at my graph here when I extended it, that's approximately where I was crossing there. If I had an actual straight line, you would see that. So the x-intercept of y is equal to absolute value of 3x plus 1 is also the x-intercept of y is equal to 3x plus 1. So you can see that they would both have the exact same x-intercepts. When we have that, we call that an invariant point. So when the absolute value and the regular linear equation have that same point in common, that same x-intercept, we call that the invariant point. So that invariant point would be at negative 1/3 and 0 on this graph. So our step 3 then is to reflect in the x-axis the part of the graph of y is equal to 3x plus 1 that is below the x-axis. the V-shape graph that results is the graph of y is equal to the absolute value of 3x plus 1. So if I extend my graph here, whoops, my points are, I should probably count my points, that'll make it better. Okay, so I went over. So when I continue this line down this way, when I reflect that into the x-axis, so I reflect those points, so my points were at -1 and -2. So to reflect that, I would have my y, because I'm reflecting in the x, so my y would be the one to change. So -1, -2 reflected will become -1, +2. So this point here is now going to be up here at -1 and 1, 2. So my next point, which was at -2 and -5, is now going to be at -2 and 5. And then my other point that I had here at -3 and -8 is going to be at -3, +8. So now this graph here is going to be our reflected, or that's going to be the graph. So my V that I've made on the top there is my graph of y is equal to the absolute value of 3x plus 1. Okay, so now it says state the domain and the range. So my domain, I can use any value that I want for my domain. So it's the set of real numbers. For my range, though, my graph was greater than or equal to 0. And y is an element of real numbers. So invariant points, it says, are the points that remain unchanged when a transition is applied. What other points on the graph are invariant points? So if you take a look at this, invariant point means that they are the ones that stay the same. So if we take a look, then the ones on this right branch, this whole side here, would be invariant points because they are in common to both of the original equation and the absolute value equation. So the entire right branch would also be an invariant point. The right branch was first constructed by graphing y is equal to 3x plus 1. If the left branch was constructed in this manner, what would the equation be? So y is equal to 3x plus 1 gave us the right side. So to graph it on the left side, that would mean we'd have to have a negative value. So we would have either y is equal to -3x minus 1, or y is equal to -3x plus 1 in brackets. Since the right branch is the equation of y is equal to 3x plus 1, and the left branch is from the equation y is equal to -3x minus 1, the graph of y is equal to absolute value of 3x plus 1 can be described as a piecewise function. So we have two parts to the graph. So we have y is equal to then on one side, 3x plus 1 when our x value is greater than or equal to negative 1/3 and negative 3x minus 1 when x then would be less than negative 1/3. Okay, so I've just taken that from that invariant point, that negative 1/3. So if you look on the graph, when it was equal to y is equal to 3x plus 1, x had to be everything greater than or equal to that 1/3, sorry, negative 1/3. And it's a little bit hard to tell from here where that would be, but my dot should be there. Well, oops, my alignment's off. It's right at that point in that B. So at negative 1/3, my graph is positive, right? On the other side of that, it's negative, or negative slope, if you want to think of it that way. Okay, the next example says, sketch the graph of y is equal to absolute value of negative 1/2 x minus 4. State the domain and range and express as a piecewise function. Okay, so the first thing you have to do is just drop that absolute value sign and sketch that graph. So first we sketch y is equal to negative 1/2 x minus 4. So that means for this one, your slope is equal, or your y-intercept is equal to negative 4, and your slope is equal to, which would be negative 1/2. Okay, so we'll graph that first. So my slope was at, or my y-intercept was at negative 4. And then my graph, or my slope went down 1 over 2. And then it would be down 1 over 2, whoops, down 1 over 2, down 1 over 2. So then I can calculate my x-intercept. So my x-intercept, we let y equal 0. Then we have 0 is equal to negative 1/2 x minus 4. So 4 is equal to negative 1/2 x multiplied by negative 2. That gets rid of that. So I have negative 8 is equal to x. So my x-intercept is at negative 8, 0, which means that is my invariant point. That's the point that's going to be exactly the same in both graphs. So negative 8, 0 is going to be way over here. I'll do my invariant point. Whoops. There's negative 8. So negative 8. So once we have that invariant point, then we reflect the part of y is equal to negative 1/2 x minus 4. That is below the x-axis. So whatever is below there, so that would be all of these points in between my purple and my blue dot, I have to also reflect those in the x-axis. Okay, so first what I'm going to do here is I'm just going to continue to draw in my dots between the blue and the purple here. So it was negative 1/2 slope, so if I go up 1, that means I have to go to the left 2. Okay, and that puts us right there. So now anything that is below has to be reflected above. So right here then, this point here was at, and I can't see my numbers on the smartboard, but it's going to be a -6 and -1, so that goes at 6, 1. Whoops, let's do red. So those are my reflected points. So this one was at -4, -2, so it's going to be at -4, +2. This one here will be at -2, -3. Where's that? -4, 0, 2, and I can't see my numbers. I think that's a 5. Six and 4. Okay, you get the point there. But now, because this line here, my blue line, if I continued it above the x-axis, would still be going 1, 2, 1, and then 1, 2, 1, say over there. So this line here would be the one branch, and now this line here is the other branch. So that, my blue, is the graph of the absolute value function. So first you graph the function without the absolute value, then you find your invariant point, and that's the point that's going to be common to both the graph without the absolute value and the absolute value graph. Then you plot your reflection points and make your V. So our domain for this is a set of all real numbers. Our range for this one, y has to be greater than or equal to 0, and y is an element of real numbers. So the piecewise function then. So when we graphed, leave it like that and just write a little smaller. So piecewise function, so y is equal to -1/2 x minus 4. So that was that one part of the graph that we drew when my x values were greater than or equal to -8. So at -8 here, that's where I get, sorry, I said, let me finish writing it. So when x is less than or equal to -8, so if I look on this side, and I'll just highlight here, when I look on this side here, that is the graph of -1/2 x minus 4. So that is this graph here. So when I have values less than -8, I am drawing the graph of -1/2 x minus 4. When I'm looking at on this, I'll call this my green side of the graph, so this side here, my x values are larger than 8. They're larger than -8. So that's going to be when x is greater than -8. We don't use the equal to, we only use the equal to in, or for the part of the graph that we had initially, the linear part we had initially sketched. So what is it on this side then? Opposite signs. This was -1/2 x minus 4, so this is going to be 1/2 x plus 4. And if you check this, my y-intercept is at +4. My slope, I went up 1 over 1, 2. Okay, so that's it to doing the graphs when you have your a value inside the bracket. So our next part then, I'm just going to pause here while I flip to the next one. We'll do the absolute value functions of degree 2. forgot to turn the volume on there for the first minute. So what we're looking at is absolute value functions of degree 2, which means we are graphing functions that are quadratic. So the general form of this is fx is equal to absolute value of ax squared plus bx plus c. So we're going to work our way through this graph, through this by actually just doing a graph. So we're looking at f of x is equal to the absolute value of x squared minus x minus 2. So the first thing we have to do then is the same thing as we did with the linear ones. We're going to sketch the graph of the function of x equal to x squared minus x minus 2. So we're just dropping off that absolute value. Once we do that, then we state the domain and range of the absolute value graph only, not of the whole graph, just the absolute value. So with the quadratic, in order to graph this, we need to find our roots for the equation. So that means we need to factor it and find the x-intercepts. So I have y is equal to x squared minus x minus 2. So product and sum says I need something that multiplies to negative 2 and adds to negative 1. So that would give me negative 2 times 1. So y is equal to x minus 2 times x plus 1. So if I want to find the roots for that, that means I have to let y equal 0. So 0 is equal to x minus 2 times x plus 1. So x minus 2 equals 0, or x plus 1 equals 0. So x is equal to 2, x is equal to negative 1. So as points, those would be at 2, 0 and negative 1, 0. So step 2 says to complete the square to find the vertex of the function. So completing the square then gives you that PQ value so that you can graph your line. And I'm going to show you two ways to do it, and depending on, unless the question specifically says, you can either do complete the square or the other method. And I have showed you the other method before for finding P and Q. So first with complete the square. So the first thing to do is I put a bracket around x squared minus x, put my plus blank, minus blank, minus 2. So then, my next step was to take whatever my b value is, I take b divided by 2 and square it. So that means for this one it's a 1. So I have 1 divided by 2, and I square it, so that gives me 1/4. So that means my blanks then, and I'll just change my color here, this 1/4 will go in here and in there. So then to factor this, I would have y is equal to, because now this, my x squared plus x minus, or plus 1/4, is a trinomial square. So my factors are just square root of the first term, square root of the last term, sine of the middle. Negative 1/4 minus 2 is equal to negative 2 1/4. Or if you change that to an improper fraction, that would be negative 9/4. So my P and Q value come from here. Because remember in vertex graphing form, we have y is equal to, oh, I'm going to cough, 1 sec. A times x minus p squared plus q. So your vertex is always at the opposite side of the p in there and q. So this one then gives me my vertex at 1/2 and negative 2 1/4. So my a value here is a 1. So that means I do my basic count, which is I go over 1, up 1, over 2, up 2 squared or 4, over 3, up 3 squared or 9. Sorry. So now that I have those things, I can graph it. And once I have my graph, then I can do the other parts of the or other steps to graph my absolute value. Okay, so I graph my parabola. So I know I've got x-intercepts at 2 and 0. So x-intercept here at 2, 0, and x-intercept at -1, 0. And then I know my vertex was at 1/2 and -2 and 1/4. So 1/2 would be about here. 2 and 1/4 puts me about there. So then I'm going to do my up and overs. So from here I'm going over 1, up 1. So that'll put me there. Over 1, up 1 will put me about there. And it's kind of in between. And then I would go over 1, over 2, up 4. And why is that going to go inside there? Oh, because I only moved over 1. That's why. So over 2 would put me at 2.5. And then up 4 would put me at, that was -2 and 1/4. So that's going to be 2 and 1/4. And I need another 1 3/4 to get me. So it would be there and about there. And then I could just, so this point here would be at 2.5, oops, 2.5 and 1 3/4. This side, I'm not going to worry about that side. My next point here, I guess I should do those. So this one here, if I was at, excuse me, if I was at, my vertex was at 1/2, if I go over 1, okay, that one's there, so I don't need that one. So let's do, I got those. I don't know if I need to do any more. If I go over 3, 1, 2, 3, and up 9. 1, 2, 3, 4. So this would be at 3.5 and 6 3/4. Sorry, I guess that should be 7 3/4. I don't think I went up high enough. Maybe I did. Close enough for this anyway. So that's my graph. Now what I have to do, if you remember when we did the linear one, we reflected in the x-axis the part that was below the x-axis. So the part of the graph that was below the x-axis got reflected in the x-axis. So for this one, my x-axis, I'm just going to put it so it highlights a little bit better. The x-axis is in here. So now anything that is below that x-axis, I'm going to reflect into the x-axis. So my vertex here was at 1/2 and -2 and 1/4. So it's going to stay at 1/2 on the x, but now it's going to be positive 2 1/4. So about right there. This point here that went over 1, what were those points? So these points here are going to do the same. They were at, I think that was supposed to be 3/4 or something, so they'll be about, I'm just going to approximate them, they're 1 and a little bit. And this one, so that one was about right there. And my points, yeah, they're close, but they're not perfect. It's hard to draw it on here. So now this part here is the reflected part. My invariant points are my x-intercepts, so that's going to be here and here. The rest of my graph is going to be these points going this way. So that my green part is the graph of the absolute value. I'm just going to pause for a second because I got a coughing fit here. Okay. So I know I don't have my points accurately on here. I've something in here. I don't know if I put those exactly where they were supposed to be, but the point of it is that whatever is below in my original graph that I have done, so this part here that is below the x-axis has to be reflected in above, and then your branches that you would have had are going to stay the same. Okay, so once you finish the reflection, then you can finish the other parts here. So it says reflect the x-axis in the part, we've done that. The negative y values in the original parabola will have the absolute value applied to them, making them positive. So that's why these ones that were down here, when they're up here, because they've got that absolute value applied to them, will be positives. And that's why we won't have any in our absolute value graph going below that x-axis. So the part that was below the x-axis is reflected above. So our vertex here is now at 1/2 and positive 2 1/4. Well, that's all right. It's close. I'm more at 2 1/2 than 2 1/4. So our domain then, for our absolute value graph, I can use any x value that I want. My range has to be everything that is greater than or equal to 0. So doing this now as a piecewise, it says the absolute value graph is actually a combination of two parabolas. What are the quadratic functions of the two parabolas? So for this one, we have our left branch, actually it's our left and right, I should put them both together just to save some space. So the left and right branch are the graphs of y is equal to x squared minus x minus 2. And the middle branch is equal to the negative of that. So y is equal to negative x squared minus x minus 2. Or if you wanted, you could rewrite that as y is equal to negative x squared plus x plus 2. So another way to say this is if this is the graph of the function of x, then this would be the graph of the negative function of x. So it says we can define the absolute value function as a piecewise function of two quadratics. So the first one is y is equal to function of x, and that's when x was greater than 0. So that was giving us everything to the right side branch, negative f of x, when x was less than 0. Or you could write it as x squared minus x minus 2 when x was less than negative 1 and greater than or equal to, whoops, that should be a positive 2. So if you look on here, go back to your page, when x was less than negative 1, so less than negative 1 is that's when we're hitting all of these points here. Then it was x, part of that x squared minus x minus 2 graph. When it was greater than 2 or equal to 2, then we had, well, that should be less than or equal to 1 on that one. So this side of the branch here, then we had that x squared minus x minus 2. So then the part in between negative 1 and 2 was where we had the negative function. So that little bit of the upside down parabola. So negative x squared minus x minus 2 when we were between negative 1 and 2. Oops, don't need a bracket there. Okay, so let's try this for another one. We're going to sketch the graph of y is equal to the absolute value of 2x squared plus 3x minus 9. Now I said I was going to show you another way to do this without completing the square, so I'll do both here. So first thing we have to do is sketch the graph of 2x squared plus 3x minus 1. So first thing we had to do was factor this to find our x and y intercepts. So that's what I'll do first of all. So we'll use slide and divide. This becomes x squared plus 3x minus 18. So if I factor that, I'm going to have x plus 6 times x minus 3. So 0 is equal to x plus 6, or 0 is equal to x minus 3. So x is equal to negative 6, or x is equal to positive 3. Oh, sorry, I forgot to do my divide. Silly me. So I should have divided by 2 here. So I have y is equal to x plus 3 and 2x minus 3. So x plus 3 equals 0, or 2x minus 3 equals 0. So x is equal to negative 3, or x is equal to 3 halves. So that means negative 3, 0, and 3 halves, or 1.5, and 0 will be my invariant points. So step 2 then was to find your vertex. So you could do complete the square with this one, or you could use your other formula that we did, and I showed it to you, and I'm not sure how much we actually used it back in the chapter 5. But what you could do then with finding the vertex, you could do complete the square. And if you do complete the square on this one, you have to remember you have to factor out that 2 from there before you can do completing the square on there. So the other one is to use the PQ formula. So P is equal to negative B over 2A is our formula. So this would be P is equal to, B is a 3, so that's going to be negative 3 over 2 times 2. So that's going to be negative 3/4. Q is equal to C minus AP squared. So that means Q is equal to C is negative 9 minus 2 times, oops, P was negative 3 over 4, all squared. So Q is equal to negative 9 minus 2 times negative 9 over, oops, 8. Sorry, that'll be a positive 9. So Q is equal to, 2 goes into there 4 times, so I have 9 minus 9 over 4. Okay, so that leaves me with, if I put that, that's going to be 36 over 4 minus 9 over 4 is equal to 36 minus 9, 27 over 4. Okay, I'm just going to pause and check my math here because I seem to have a different answer than I have on my sheet of paper. Found my mistake, and I did have it right to start with. This should have been 9 over 16. When I square 3/4, it turns into 9 over 16. So that, when it cancels, will be minus 9 over 8. So this becomes 72 over 8 minus 9 over 8. So that leaves us with 80, no, not 80. $72 minus 9, 63 over 8. Yeah. Okay, just double checking my math. Oh, now I see my mistake. This should be a negative 9. 81. Wow. Sorry about that. Okay, so that should be a negative 81 over 8. So my vertex then, I'll write this over here. So my vertex ended up being at negative 3/4 and negative 81 over 8. So I'm just going to put this into a decimal just to make it easier to draw on here. So this becomes negative 0.75, and 81 over 8 is negative 10.125. So my A value here is a 2. So that means my up and over will be doubled. So instead of going over 1, up 1, I go over 1, up 2. Over 2, up should have been 4, so it'll become 8. Over 3, up should have been 9, so it'll be 18. So now we graph this. So our vertex was at negative 0.075 and negative 10.125. So 10 is here, I think. So approximately there. That's your vertex. My x-intercepts occurred at negative 3, 0. And at 3 over 2, so 1.5 and 0. So if I do my up and overs, so over 2 put me at 1, 2, whoops, and then I didn't, yeah, over 1, or sorry, over 1 put me at 0.25, and up 2 put me there. So that was at 10.125. If I go up 2, I'll be at negative 8.125. And then this way it was at 0.725, so I'm going to write that down just for plotting later. So this is, this will be at negative 0.25, and then I went up 2, so that'll be negative 8.125. So going this way, I'm going one more over. It was at negative 0.75, so it's going to be at negative 1.75. And then up 2 will be at that negative, so negative 1.75 and negative 8.125. And I'm just going to do those 2 points because if I try to plot more than that, it's just going to look ugly. So it's just to give you the general idea. So what we need to do then is anything that is below the x-axis will get graphed above. So my vertex here was at negative 0.75 and negative 10.125, so it's going to be at negative 0.75 and 10.125, so right above there. Then my invariant point here was negative 0.2, or my other point was negative 0.25, so then it'll be at positive 8.125. So 0.25 and 8.125 will be right there. And then on the other side it was at negative 1.75 and 8.125. So then my graph of the absolute value function will do this, and then it'll be this. And none of those points that I put on those branches are exact. So everything, my original graph for that 2x squared plus 3x plus 9 would have been this. Whoops. Oh, it didn't change color on me. Why is it not undoing? Okay. I seem to have a frozen screen. So, anyway, the part that's going below here, now I'm moving my points around. These points below the graph are would be from 2x squared plus 3x minus 9. And then the points above the graph, I don't know why everything's frozen right now. That's kind of a pain in the butt. Anyway, everything below there is going to be, everything below the graph would have been from the original graph without the absolute value sign. So the reflection and the branches of the arm are going to be the actual absolute value graph. So our domain for this, if it lets me move. Okay, unfroze. So what I was saying before, I'm just going to draw this in the purple here. Whoops, oh that was bad. So the purple part here would be your original graph, and then anything that's below it, so anything below here, had to be reflected above. So that's the reflection. My blue part, the blue upside down parabola is the part that was reflected below, and then the branches are the invariant points, so they stay the same. So my domain for this, I can use any real number. My range, probably see a pattern, has to be greater than or equal to 0. I can't go below 0 on an absolute value graph. So for the piecewise function, so y is equal to 2x squared plus 3x minus 9 when x, so that's the right branch and the left branch, so when x was less than negative 3 and x was greater than or equal to the other invariant point, which was at 1.5. Then for my parabola part, that's the negative part of the graph. and that was when x was in between those two. Okay, so when you're doing these, the important part is to first of all remember to draw the graph without the absolute value signs, and then anything that is below the x-axis you need to reflect into or above the x-axis. And you include your invariant points. Your invariant points help keep your graph with some accuracy to it, and your vertex. You always want to have a vertex. So x-intercepts and a vertex is what you're looking for, or if it's just a linear one, just a y-intercept.